logarithmic functions are the inverse of exponential functions, which means that all the log function does is switch the input and the output for the exponential function. So the notation's right here. Y is log base a of x if and only if a to the y equals x. As you can see, for the logarithm, x is the input, y is the output. For the exponential function, x is the output, y is the input. So the function just switches those two things. But they mean the exact same thing. This expression and that expression say the exact same thing. They both tell you what power you have to raise the base to, a, in order to get x. So like, for example, there was the binary log base 2 of like 16. This is asking, or this is expressing, what exponent do you have to raise 2 to in order to get 16? And 2 to the 4th power is 16. So the exponent is 4. And that's because 2 to the 4th equals 16. So logarithms give you exponents. It gives you the exponent that you have to raise the base to in order to get that number right there. But these two are saying the exact same thing, just in two different forms. And just like exponential functions, this is only valid for the real numbers if you have a positive base and if x is positive. There's a few reasons for that. If a is positive, then you can't raise a positive number to any power and get a negative number. So x has to be positive since a is positive. And just like with exponential functions, you could have negative bases. You could have like log base -2, and it does crazy things as a complex function with imaginary values. But we care about the real numbers, and so we're not going to go there. Some properties. These first two properties are just really stating the inverse property of exponents and logarithms. So a raised to the log base a of x is just x, because the exponent and the logarithm are inverse functions, so they undo each other. Likewise, this is doing the exact same thing. The logarithm and the exponent are inverses, so they cancel out. One more way to look at this is this logarithm is asking you, what power do you raise a to in order to get a to the x? Well, the answer is right there. You raise a to the x power to get a to the x. So the answer is x. And then these properties down here, these are the big properties. These are the ones that make logarithms so useful. Logarithms were invented by John Napier in like 1618, maybe 1619, I forget the exact date. But he invented these logarithms pretty much to simplify expressions. So with logarithms, you can turn a product into a sum. You can turn a power into a product. You can turn a quotient into a difference. Everything gets one step easier. It takes complicated things and turns them one step easier. And in the days before calculators, using logarithms and their properties is how you would do large, complex calculations. And log of any base of 1 is 0, because a to the 0 is 1, right? Those two expressions say the exact same thing. Let's just prove one of these properties. It's always fun to prove things. Let's just prove the first property there, that the log of x times y equals log x plus log y. Just kind of get a feel for how really these are just properties of exponents, just written in terms of logarithms, which makes sense since logarithms give you the exponent. So logarithms are pretty much just exponents. So let's prove this. Let's do a quick proof. To start off, let's let log base a of x equal like b, and log base a of y we'll call c, where a, x, b, c, they're all positive numbers. That means then if log base a of x is b, it means that a to the b equals x. Just write that logarithm in exponential form. If log base a of y is c, that means a to the c equals y. And now we go to our actual property. So that means that log of base a xy, which is the left side of our property there, is equivalent to log a x is a to the b, y is a to the c. We know that when you multiply two terms of the same base, you add their exponents. So that equals log base a to the b plus c. And now this we can evaluate, because this logarithm is asking you, what power do you raise a to in order to get a to the b plus c? Well, the answer, of course, is b plus c. Right? You raise a to the b plus c power if you want to get a to the b plus c. And since we know that b is log of a is a log base a of x and c is log base a of y, we can write that like so. Given us our proof, we have proven that log of xy equals log of x plus log of y. And the other proofs are similar. You just essentially start off like this and rewrite the terms with exponents and then use the property of exponents. If you see, this proof uses the sum property for exponents to prove the sum property of logs, because they're pretty much saying the same thing, just in different versions. Now, our main interest with log functions, of course, will be their derivative. So, let's proceed to that. Although actually, we aren't going to mess around with many bases for log functions, like log base 10, log base 2. We won't touch those much this year. Instead, we'll almost entirely concern ourselves with the natural log function. The natural logarithm. The notation is y equals log x. You could say ln x, but I just say log x because this is the main logarithm. So this is just y equals log x. And this is the inverse to e to the x. Right, so this is log base e. E is the base of the natural log function. Although, as I mentioned, this function was studied decades before e. Like, e was in the 1680s when Bernoulli was doing his study of interest and how much money you can make after 1 year if you invest $1 at 100% interest, because the more often you compound your interest, the more money you make, and the answer was E dollars. That was the most that you could make. That, I believe, was the first study of E. Natural log was in the 1640s by this guy named St. Vincent was his last name. And he was studying this not in terms of E, of course, because E didn't even exist yet or hadn't even been discovered yet. Instead, the person who first studied logarithms, St. Vincent, I forget his first name, but it's like Gregory or Germain, or it's G something. What he was studying was the area underneath the hyperbola 1 over t. Right, this is a hyperbola. He only cared about the positive space. And what he was really studying was the area from 1 until some value, we'll call it x. And he realized that the area underneath this curve had the same properties of logarithms, which Napier had just discovered a few decades before. And so at first, this function that gave the area underneath that curve from 1 to x was called the hyperbolic logarithm, but it turned into the natural log function. And in fact, the main way to define the natural log of x is as the area underneath the curve from 1 to x, where the curve is 1 over t. We haven't studied integrals yet, but most of you have already seen them. So this expression right here gives the area underneath that hyperbola from 1 until x, and that is the natural log. And E is the number such that the area from 1 until e is exactly 1. So e is the number that if you start from 1 and go until e, this area underneath that hyperbola is exactly 1. So that is one way to define the natural log function. It's the main way to define the natural log function. And all of these properties can be proven with that definition. But since we haven't learned integration yet, our definition will just be up here. Log x is the inverse to e to the x. So now that we've established that, let's differentiate this thing. So the derivative of natural log. So since the natural log of x is the inverse to e to the x, we can write this down right here. E to the log x equals x. Because again, if you plug an inverse into its original function, they cancel out. So e and log are inverse functions, they cancel out and just give you x. We can differentiate both sides of this expression. Now the left side needs the chain rule. So the derivative of any exponential function is just itself times the derivative of the exponent, which we don't know yet, so we'll just write that down like this. It's e to the log x times the derivative of log x. The right side differentiates to 1. Our goal is to solve for this, right? We want to solve for the derivative of log x, so we divide both sides by e to the log x. And there's our answer. Although it makes sense to write that in a little bit nicer form, since e to the log x equals x, the derivative of log x equals 1 over x. This is kind of cool, by the way. This is the first function we've seen so far that changes what kind of function it is after differentiation. Like exponential functions, when you differentiate, stay exponential. Polynomials stay polynomials. Trig functions stay trig functions, but this logarithm turns into a rational function. It changes what type of function it is, which is pretty cool.